You load a tool, write the G-code, and press start. Sometimes you get a perfectly smooth mirror finish. Other times, the machine chatters, the material burns, or the tool snaps in half. The difference between a perfect cut and a scrapped part comes down to how you control motion. A CNC machine relies on 3 distinct types of motion: rotary speed, measured in RPM, linear edge speed, or cutting speed, and translational advance, called feed rate. To see how they interact, think of a merry-go-round. If you stand dead center or hang off the outer edge, you complete one full rotation in the exact same amount of time. That is your RPM. But the physical experience is completely different. The person on the outer edge travels a much longer physical distance in that same single rotation. Their linear speed, the distance covered per minute, is much higher. In machining, that linear edge speed is your cutting speed. Now push that spinning merry-go-round in a straight line across the playground. That forward motion pushing into the material is your feed rate. Confusing these variables leads to tool failure because each one handles a different stress. Cutting speed defines the thermal limits at the tool's edge, making it the primary baseline you need to calculate an appropriate RPM. Your ideal cutting speed depends on 3 physical constraints: material hardness, cutting tool material, and desired surface finish. Soft materials like aluminum paired with tough carbide tools allow for high cutting speeds. Hard materials like steel paired with high-speed steel tools require you to slow right down to protect the cutting edge. Tool manufacturers provide your target cutting speed in surface feet per minute, or SFM, but your CNC machine only speaks in RPM. To translate, you use the imperial formula. Multiply your target SFM by 12, then divide that by pi times the diameter of your tool. If you look at a shop floor cheat sheet, you rarely see that full equation. Instead of typing pi into a calculator every time, machinists divide 12 by 3.14159 to create a constant. That gives you 3.82, simplifying the formula to 3.82 times SFM divided by diameter. If you operate in metric, the logic holds, but the math shifts. When working with surface meters per minute, or SMM, the constant changes to 318. Knowing where these constants come from keeps you grounded. If you understand the math, you avoid formula memorization errors, and you won't blindly plug metric tool diameters into an imperial formula. Let's run the numbers for a standard milling operation. You are cutting aluminum with a recommended target of 800 SFM. Using a half-inch end mill, you multiply 3.82 by 800, then divide by 0.5. You program your spindle at 6,112 RPM. Now you try one. You have a 1/4-inch drill bit going into mild steel. The manufacturer recommends 100 SFM. What is your programmed RPM? You multiply 3.82 by 100 and divide by 0.25, giving you 1,528 RPM. Drilling utilizes the exact same mathematical principles as milling. But the moment you move to a CNC lathe, the rules of the diameter change. On a mill, the tool spins, so D is the diameter of your cutter. On a lathe, the workpiece spins. D is now the diameter of the material itself. As your lathe tool cuts deeper into the part, the diameter of the material shrinks. To maintain a constant surface speed on the cutting edge, modern lathes use a feature called CSS. The machine automatically accelerates the RPM as the tool approaches the center. Getting the diameter wrong, or choosing the wrong target speed, has immediate physical consequences. Run too fast, and the excess heat will melt your chips and break the tool. Run too slow, and the tool rubs against the material, work hardening the surface and ruining the finish. Correctly identifying exactly which diameter to measure prevents these setup errors and keeps your cuts clean on the shop floor. To get this right every time, build a habit around this 5-step workflow. Step 1. Identify your material and tool. Step 2. Find your target SFM. Step 3. Choose the correct formula. Step 4. Verify your diameter variable. Step 5. Calculate your final RPM. Following this exact sequence removes the guesswork from your spindle settings. It ensures your tool works within its design limits, giving you a repeatable, reliable process for every job you set up. If this breakdown helped clarify your machining process, Hit the like button and subscribe to learn and grow with fun for more practical engineering guides.